Have you ever looked up at the stars and noticed them twinkling? This twinkling, known as scintillation, is caused by the Earth's atmosphere. A similar phenomenon, ionospheric scintillation, affects radio signals passing through the ionosphere. The ionosphere is ionized by solar radiation. Radio signals scatter and fluctuate in this charged layer. This effect is stronger in polar regions due to increased ionization. Ionospheric scintillation is essentially the rapid fluctuation of radio signals passing through the Earth's ionosphere. Imagine the twinkling of stars, but instead of light, it's radio waves that are being affected. These fluctuations can cause significant problems for a variety of technologies that rely on radio signals, including GPS navigation, satellite communication, and radio astronomy. The severity of ionospheric scintillation can vary depending on factors such as the time of day, the season, and the level of solar activity. During periods of high solar activity, such as solar flares and coronal mass ejections, the ionosphere becomes more turbulent, leading to more frequent and intense scintillation events. Understanding the causes and behavior of ionospheric scintillation is crucial for mitigating its impacts on our technology-dependent world. By studying this phenomenon, scientists hope to develop better forecasting and mitigation strategies to ensure the reliability of the communication and navigation systems we rely on every day. The ionosphere is a dynamic region of the Earth's atmosphere crucial for our planet's habitability. Located between 60 and 1,000 kilometers above the surface, it has a high concentration of ions and free electrons. Solar radiation ionizes atoms and molecules, creating charged particles. The ionosphere consists of several layers, D, E, and F. These layers vary in altitude and electron density. The ionosphere acts as a shield, absorbing harmful UV and X-ray radiation. The polar cap region, at Earth's highest latitudes, is susceptible to ionospheric scintillation. This is due to the unique configuration of the Earth's magnetic field lines. In polar regions, the field lines are nearly vertical. Solar wind interacts with the Earth's magnetic field, funneling charged particles into the polar regions. This leads to enhanced ionization and irregularities, creating ideal conditions for scintillation. Space weather and scintillation. Space weather, the ever-changing environmental conditions in space, plays a crucial role in driving ionospheric scintillation. Solar flares, intense bursts of energy from the sun, can release vast amounts of radiation and charged particles into space. When these particles reach the Earth, they interact with the ionosphere, increasing ionization and creating disturbances that can lead to scintillation. Coronal mass ejections, or CMEs, another type of space weather event, are massive eruptions of solar material from the sun's corona. CMEs can travel at speeds of millions of kilometers per hour and carry billions of tons of plasma. When a CME impacts the Earth's magnetic field, it can trigger geomagnetic storms, which are disturbances in the Earth's magnetic field. These storms can cause significant disruptions to the ionosphere, leading to widespread and intense scintillation events. Understanding the relationship between space weather and ionospheric scintillation is crucial for predicting and mitigating the impacts of these events on our technological infrastructure. Impacts of ionospheric scintillation. Ionospheric scintillation can have a wide range of impacts on our technology-dependent society. One of the most significant impacts is on satellite communication systems. Scintillation can cause signal fading and dropouts, disrupting communication links and reducing the quality of satellite TV, internet, and phone services. Navigation systems, such as GPS, are also vulnerable to scintillation. The accuracy of GPS positioning relies on the precise timing of signals from multiple satellites. Scintillation can disrupt these signals, leading to positioning errors and reduced accuracy. This can be particularly problematic for applications that require high-precision positioning, such as aviation, maritime navigation, and precision agriculture. Radio astronomy, which uses radio telescopes to observe celestial objects, is another field affected by ionospheric scintillation. Scintillation can introduce noise and distort astronomical signals, making it difficult to study distant galaxies, pulsars, and other celestial objects. Current challenges and gaps. Despite significant advancements in our understanding of ionospheric scintillation, several challenges and gaps remain. One of the main challenges is the complex and dynamic nature of the ionosphere itself. The ionosphere is constantly changing in response to solar activity, geomagnetic conditions, and other factors, making it difficult to predict scintillation events accurately. Another challenge is the lack of comprehensive global observations of ionospheric scintillation. While ground-based GPS receivers provide valuable data, they only offer a limited view of the ionosphere. Space-based observations from satellites are essential for obtaining a global perspective on scintillation patterns and behavior. The development of accurate and reliable scintillation forecasting models is another area where further research is needed. Current models often struggle to capture the complex interplay of factors that contribute to scintillation, leading to uncertainties in predictions. Future research directions. To address the challenges and gaps in our understanding of ionospheric scintillation, several future research directions are crucial. One promising area is the development of advanced ionospheric models that incorporate real-time data from ground-based and space-based sensors. These models could provide more accurate and timely forecasts of scintillation events, enabling better mitigation strategies. Another important research direction is the development of new and improved mitigation techniques. This could include developing adaptive signal processing techniques that can compensate for the effects of scintillation, or designing more resilient communication and navigation systems that are less susceptible to scintillation-induced disruptions. Further research is also needed to better understand the fundamental physical processes that drive ionospheric scintillation, particularly in the polar cap region. This includes studying the formation and evolution of plasma patches, the role of space weather events, and the interaction between the ionosphere and the neutral atmosphere. Mitigation and prediction. Mitigating the impacts of ionospheric scintillation is crucial for ensuring the reliability of our technological infrastructure. Several techniques can be employed to reduce the effects of scintillation on communication and navigation systems. One common technique is to use multiple frequencies. By transmitting signals on multiple frequencies, the impact of scintillation can be reduced, as the different frequencies are affected to varying degrees. Another mitigation technique is to use adaptive signal processing. This involves adjusting the receiver's signal processing parameters in real time to compensate for the distortions caused by scintillation. This technique can be effective in reducing the impact of scintillation on signal quality. Accurate prediction of scintillation events is essential for implementing timely mitigation strategies. By forecasting when and where scintillation is likely to occur, operators of communication and navigation systems can take steps to minimize disruptions. This could include switching to alternative frequencies, adjusting signal processing parameters, or scheduling critical operations during periods of low scintillation activity. The importance of continued research. Continued research on ionospheric scintillation is crucial for several reasons. First, as our reliance on space-based technology continues to grow, so too does our vulnerability to the impacts of scintillation. Understanding and mitigating these impacts is essential for ensuring the reliability of the communication, navigation, and remote sensing systems that underpin our modern world. Second, ionospheric scintillation research can provide valuable insights into the fundamental physics of the ionosphere and the Sun-Earth connection. By studying the causes and behavior of scintillation, we can gain a better understanding of space weather phenomena and their potential impacts on our planet. Finally, research in this field has the potential to lead to the development of new technologies and applications. For example, by understanding how ionospheric scintillation affects radio signals, we may be able to develop new techniques for remote sensing of the ionosphere, or even for detecting and tracking objects in space. Conclusion. Unveiling the mysteries of the ionosphere. Ionospheric scintillation, a fascinating phenomenon that occurs when radio signals pass through the Earth's ionosphere, poses both challenges and opportunities. While scintillation can disrupt critical communication and navigation systems, it also offers a unique window into the complex and dynamic nature of the Earth's upper atmosphere. Through continued research, we can deepen our understanding of the causes and behavior of ionospheric scintillation, improve our ability to predict and mitigate its impacts, and potentially unlock new technological advancements. By unraveling the mysteries of the ionosphere, we can ensure the resilience of our technological infrastructure and gain a deeper appreciation for the interconnectedness of our planet and the vast expanse of space. Do you have any thoughts or experiences to share? Leave a comment. I'd love to hear your perspective.